Hi, Kate. Welcome back.
I'm so awkward.
Hi, Kate.
Congratulations on winning.
Oh yeah, we're so proud of you.
Congratulations, we love you. I wrote on the board and Mr. Brown erased it.
I have to do it again because I can't find it in the other one. I did that in the other one.
Yeah, you did. And now it's there again.
Yep.
So, Kate, I'll email you the document that we're working from, but it is just a brief summary of all concepts and such around each chapter, and then some multiple choice.
The camera quality is like really good on that thing.
It is pretty darn good, and even when it compresses at YouTube, because when you put a video up on YouTube, you can put it up in 4K. It don't matter. They compress it down to like 720. I mean, it's dramatically compressed, but it's still a very good picture in the end. I'm pretty impressed.
We should make some
Let's
YouTube
do some
videos.
whiteboarding. Just
Hi,
do
my
this
name
as
is Mr. Brown. and We're gonna be
No,
doing-
heck, we should
No,
have
this,
Mr. Brown
like-
do a TikTok.
Right. So anyway, we have an hour left.
Mr.
Fly.
Brown, hit the wall.
That's what I was gonna say.
We have an hour left.
Wait,
We're
no,
moving.
please.
No.
Do you know how to?
I don't know what you're talking about. Hit the whoa.
like
You like throw something up
Yeah,
and
and
then
then
you
you
catch
catch
it
it.
and then you.
Wow. Could you just show
you
them a video?
technically did it.
They're really laughing.
Wow.
Wait, can I please record you doing that?
No, it's already recorded. Download it on YouTube later. Just
No,
check it
that's
out.
such a hassle.
Your life's a hassle. Welcome to physics. This is the professional start of the video. We will just cut off all the rest. Hi, Kate. Welcome back. Congratulations on winning. So we're going to
Background.
let's go through this. So we're going to move quickly through the concepts, and I'll give you a couple of minutes on the multiple choice in each section. We will not finish every section today, but hopefully we'll get close enough, and we'll see how far we get. First one, constant or variable. Why did I put constant or variable under forces? Why does that matter?
Because if it's variable, then you can't. Then the acceleration is changing.
If it's variable, the acceleration is changing. So then what the heck? What do you do with something that is variable?
You can't use your kinematics equations.
You cannot use your kinematics equations. And so if you see a force and it looks something like any of these, right? These are variable forces. The first two vary with what variable?
X.
Displacement, like a spring, right? This one varies with velocity, air resistance. This one varies with time. And so maybe there's an engine or something and someone slams the gas or whatever, and there is a time dependent. That was not funny. I could have almost fallen and sprained my ankle.
That's not funny.
Wait a minute, that's what I just said.
Honestly, if I saw you fall on the stairs, I would just laugh. Like, I just laugh every time someone falls.
So whenever you out yourself as a cold-hearted person, this does nothing to elevate.
It's so funny when someone is walking in the halls and then just randomly
Mahek,
trips.
elevate love,
It's so. It was
not
traumatic.
victimizing others.
Like, okay, one time I was like walking.
Physics. So if you see any of these forces that are variable, you must think instantly in your mind, oh, I'm thinking calculus. Okay, calculus is what I need because these do not have a constant acceleration. If you don't have a constant acceleration, you cannot do your basic kinematic stuff. You must divide this force by mass to figure out what the acceleration would be and then start integrating.
You really
Okay.
should put more room on here.
No, I should not. We're okay. And so next to constant or variable, you can just put down, hey, if it's variable, calculus. Okay? And so
Mahek,
this is
I
meant to be
can-
a quick word association just so that you can kind of categorize your knowledge. And there's quite a bit of room off to the right. Conservative, non-conservative. What do those two words mean when we're talking about forces in physics? Conservative forces, non-conservative forces.
If
Like,
Like it's
like
maintained, like
heat
spring.
is dissipated or stuff.
Losing energy.
Spring forces are.
constant or not.
Okay, so forces that do not, forces that are, here's the official definition of conservative. If it's path independent. If it doesn't matter how you got from point A to point B, if it's a path independent integral, if you will, okay, that is a conservative force. So conservative forces would be gravity. Conservative forces would be springs. Conservative forces would be, we don't deal with magnetism and electrical currents or charges, positive and negative repelling the way you have in atoms in chemistry, but they would also fall under the same umbrella. Those are conservative forces. Forces that are not conservative, like friction, air resistance, right? Anything where it actually matters the path that you take because you're having a resistive force along with you. And so just something to kind of keep in your mind, when I'm looking at a force problem, I'm instantly trying to make a decision, almost like a flow chart in my head. Is this calculus because it's variable, or is it constant and probably not calculus? Is this a conservative or non-conservative force? Let me try and think. Because if it's conservative, energy might be the best way to go. Okay, if it's non-conservative, I gotta wonder, do I know how much energy is being dissipated because of heat, or do I not? The third bullet applies to every single free response question in AP Physics when you get lost. What do they ask you in the part right above this section? If you get lost on an AP question, I have no idea how to do this. How can I do this with the stuff they gave me? Go look at the part above, because if you're on part C, whatever part B asks you to find, odds are you're going to use B to find C. Not always. But look at the part above and see if it'll help out. Okay, next is a definition of force. Force is a quantity that changes velocity. Really simple. Next bullet point says inertial reference frame. What is that talking about?
Frame of reference.
It's not a force diagram. It is a frame of reference. Good job. It has the word frame in it. Fantastic.
And reference.
And it has the word reference. Good job. Yeah.
Yeah.
It's an inertial frame. What is an inertial reference frame?
It's like when the stuff is moving, is it like moving together?
An inertial reference frame means that you're at equilibrium. An inertial reference frame means you're not accelerating. That's the first thing I need you to know about an inertial reference frame. The second thing I need you to know is that Newton's laws hold in an inertial reference frame. Newton's laws do not hold in a accelerating reference frame. If you are on a ride at Six Flags, like you're on the roller coaster, you may feel like there's a fictitious force, imaginary force pushing your head down when you go into a loop. And there's not. There's not. Okay? That's just the inertia of your head trying to move in a straight line. But you feel fictitious forces when you are in an when you're in an accelerated reference frame. In inertial reference frames, then F equals ma is going to work. Okay? You can use Newton's laws.
Wait, but how can F equals ma work when a equals 0?
Got it. So when you look at, if you are in an inertial reference frame, you're not accelerating. You're standing on the ground watching someone on the roller coaster. You can actually look at the person on the roller coaster, figure out the forces and their acceleration and calculate it.
So it's just
the
to
person
reference.
on the roller coaster who's being accelerated cannot properly figure out all the forces acting on them because they are going to see their inertia acting as a fictitious force, a centrifugal effect of being flung to the outside or flung down in the case of
AKA neck pain.
What happened?
Neck pain.
I got an email saying, Brown, take your attendance, dude. Hello?
It's still recording.
Of course it's recording. It's recording because this is important. Taking my attendance is important.
Well, she can't see that, so.
Shh. Hold on. That's a really interesting shot of your nose. You can see so clearly up the nostrils. Do you need to blow your nose? You got a little...
That's so
All right.
embarrassing. I was just looking at it and it looks fine.
No, you're blushing a little bit there now. It's okay. I would be too if I just look at your... So...
Kate! Don't let this slide. Turn
Slide.
the video off.
We're moving right on to friction now and sliding. So let's talk about sliding friction.
What?
So there are two kinds of friction. The first is kinetic or sliding, and it has an equal sign, right? So force of friction is equal to mu k times the perpendicular surface force or normal reaction force. And just be careful, there can be more than one normal. You've seen this already on some problems where, say, something is say a ball is rolling around in a pie pan or whatever, and it has a bottom and a side. Okay? A pie pan has a bottom surface, a side surface. And one or both may have their own frictional forces. You have to calculate the problem. Just be careful as to which normal you use. You want to put in the right normal for the right surface to get the right friction out of it. Okay? So think that through a little bit. This kind of friction is dissipating heat. This kind of friction, sliding friction, is causing surfaces to get hotter and you are dissipating kinetic energy. Okay? Next kind of friction, static. Static friction does not have an equal sign. Okay, and the only formula you get on the formula sheet is not for static and kinetic separately at this point. They have done that some in the past. They just do less than or equals to mu. Okay, and I'm going to put again a symbol for our perpendicular surface force there. I'm going to put subscripts of S, but they're not on the formula sheet. Why does the static frictional force have a less than or equal to sign? Let's remember. You've done labs with this, with pulling things with force probes, way back with our Atwood machine stuff in the fall. Why is there a less than or equal to?
Sorry, I told myself.
Oh, you're allowed to talk.
I'm scared.
You don't have to be scared because it's a recording. Is that why you're scared?
No.
Oh, you can be totally wrong. This is the exam's a month away. I almost want you to be wrong now, and then go, oh, that's what I had that was
It's
wrong.
like
I
a
got to fix
source
that.
of error.
The source of error is not why you have less than or equal to. But there was sources of error with our friction lab and stuff. We had to make sure the track was, just flat and everything else. Yes.
Because the static friction, it won't move until you get like greater than that. So like it's gonna stay like static at any value less than or equal to mu times the normal force.
Correct. So there's a graph that looks like this. Now the graph coming out of a force probe, of course, is a lot more jagged than that. That's the general shape. And this up here at the very top, if you remember, we would use our, we would look at our stats right here, and we would look at the maximum. The maximum there equals mu static times the perpendicular surface force. And so if data point down here was less than that max, what does this physically mean? So over here, I have a piece of paper on this chair where I was sitting. And if we take this paper on this chair and I begin to tip the chair a little bit, the paper has not yet fallen. So the frictional force acting to hold it in place is a little bit. If I tip it, so maybe I'm right there. I've only asked the friction to act a little bit to hold it. We're nowhere close to the limit of friction. If I tip it a little further, now I'm there. It's still not falling, but it needs more frictional force to hold it in place because I've tipped it farther and gravity has more of a component parallel to my chair. Now it's tipped farther. Now it's tipped farther. And eventually I keep on tipping and I reach that limit and it falls. And so once you exceed that limit, friction can no longer hold it in place. The less than or equal to is there because whenever you see a static frictional force, you need to ask yourself, should I be looking at the limit? Or should I be looking at how hard is right now mg sine theta acting to make it move? Friction must be equal and opposite because it's in equilibrium. It can't be equal to mu normal. That would be the limit. Right? In this case, it's just enough to hold it in place. So let me find mg sine theta, and that's friction. So that's a complicated part of friction to think about when you are looking for static friction. Okay? Probably one of the most difficult things they'll test on friction. All right? I think I just said everything except for rolling. So rolling friction is an example of static friction, and all the static friction does not dissipate heat. Meaning that if I tip this chair again with this paper in it, the paper is not giving off heat. It's not losing mechanical energy to heat as it tries to slip, but it can't slip because friction holds it in place. Because there's no rubbing of surfaces that's giving off heat. Rolling friction is somewhat like that, in that if you have a surface like this, okay, and my hoop here is rolling along, there's like one point on my hoop in contact with one point on the surface at a time. Then a new point on the hoop contacts a new point on the ground. Then a new point on the hoop contacts a new point on the ground. And as long as you have this 1-to-1 ratio, then this is considered like static friction because it's not one point on my hoop sliding along all those green points. It's a different point on the hoop each time, touching a different green point. That's static. It does not dissipate heat in a perfect physics world. In reality, everything slips a little bit, and that's why your tires get warm when you drive. Your tires also deform shape as they go around, and that's also why they get warm when you drive. But if you had tires made of metal that were this hard, that'd be very uncomfortable to drive on, but it would actually have much less heat generated by friction, but you'd probably have more heat generated by bumping and bouncing around.
And
So it'd be
slipping.
a trade-off.
Metal would slip on asphalt, wouldn't it?
Sure, metal would slip on asphalt. Metal tends not to slip on metal, like for instance, a railroad wheel on railroad tracks. Almost no friction whatsoever as it rolls down. The coefficient of friction is like 0.02 or 0.01 of railroad wheels on tracks. It's very, very low. All right, so all that to say rolling is static, and that these do not dissipate heat as kinetic energy when we're doing this. All right, hey, down below are some multiple choice. Go ahead and try them. There's 1, 2, 3, 4, and then we go on to the next page. We're gonna pause here. We're gonna let you work on those little multiple choice and have a little fun, and we'll be right back with you. Okay, so don't look at the board, Kate, unless you've already finished the 4 problems. The answers are over here on the left-hand side. You can blow that up. There's work shown for the last 3. The first one, I think, once you see the answer, it should be a little bit self-explanatory. That it has 1/3 of the mass, and therefore the tension is 1/3 of the force needed to attain that acceleration. We're going to go on to the next page. So page 2, work, power, energy. And let's take a look. I want to start with the graphic down the bottom right-hand corner, and the graphic is that of a system. And in this system, there is energy transforming within, and there is also energy transferring in and out from the environment. So just kind of verbiage. The verbiage from this book is verbiage from what I'm going to say is kind of physics education research. A lot of summary, not done by this person, but done by a lot of other people who study how people learn physics. And so this is very common verbiage to find on the AP Physics test. But there's a system of the stuff that you are considering, and everything else we call your environment. All right? And whenever there is work being done on the environment, okay, and there's energy being transferred in, the word used for work that increases the energy in my system, we use the word a transfer, not a transformation. Because something is out here in the environment is giving up energy and is increasing the energy of my system. If, on the other hand, energy is leaving my system, and rather than having work done that is positive on my system, I have work done that's negative. Maybe friction is slowing something down in my system. Okay, so this is going to be energy coming out of my system. Again, they call it a transfer. Okay, and so work and transfer of energy are pretty synonymous. As opposed to within my system, if I'm simply going from UG, potential energy to gravity, US, potential energy to spring, kinetic energy of motion, if I'm just changing within my system one form of energy to another, we call this a transformation, okay? So in here, we are transforming energy types rather than transferring. Not super duper the most important thing ever, but it helps to give kind of a big picture about it. So starting at the top with work, up at the top of the page now. Work is an integral. It is a dot product. Okay, so both force and displacement are vectors, but please note that work and energy are scalars. So when you do the integral, the dot product integral for work, you strip away the vector directional information, and you end up with a scalar quantity. So the formula is there, it's in the formula sheet, you don't have to memorize it. For a constant force, and I'll be honest, over half of the time in AP Physics, when you're required to find work, the force is constant. And so you do not have to integrate if the force is constant. You just have to do FD cosine theta, or Fx cosine theta, all right? And the cosine theta allows you to grab that part of the force that is parallel to the displacement, so that it is either moving it faster or slower, that is transferring energy in by moving it faster, or transferring energy out by moving it slower. Okay? Here's a mention again of conservative forces we saw on the previous page. So they are path independent. Gravity, and it says E and B, that's electric and magnetic fields, which you don't need to know about E and B.
Why is B magnetic?
Not today. And so I'm going to skip the next 3 points because I already said them out loud. So there's 3 things down here below where it says work is 0. Work is 0 if F and D are perpendicular, right? If F and D are 90 degrees, cosine of 90 degrees or pi over 2 radians is 0. Work is 0 if there's no displacement. That is, if you end up where you started in a conservative force field, or if you never moved at all, there is no net work being done because there was no displacement. Of course, work is 0 if nothing moves, and it's 0 if there's no net force. Okay, if there's no net force, there's no net work. You may still have individual forces doing work, but one does positive 50 joules, one does negative 50 joules, and they're canceling out in some way. Think a car with cruise control. A car with cruise control is maintaining constant velocity. It is not gaining energy or losing energy. I'm ignoring the fact you're burning fuel out of the tank. So the engine is pushing it forward, that's doing work. But also the friction of the air is dragging against it, that's doing negative work. And the two cancel out when you're in cruise control, okay? So that thought of network is important in there, and it's not written down. So I wanted to say it. Power is a drop in the bucket. If you don't remember us covering power, that's because we did it in one part of one day. Power is not a significant part of the curriculum. It's usually one multiple choice question or one part of one for response. Okay. The formulas that are on there that I'm showing you, that is F dot V as a dot product again. They must be parallel to each other. And also the power is the derivative of work with respect to time. Those are both on the formula sheet. Okay, you don't need to memorize them.
They
You
must
just need
be
to be able to hold them
parallel
out
to
and
each
apply them.
other.
They must be not totally parallel. Some
Just
part must be parallel.
not perpendicular.
Correct, not perpendicular. Yeah, thank you. So you would use a cosine if they're not parallel. And I would say every single time I've seen F dot V used for power on the AP test, they're parallel. Okay.
I have a question.
Yeah.
So for first one on the AP exam, like, it's just gonna be random topics, right? Or is like most likely gonna be over one thing?
I'm going to say yes to both. It is random topics, and if they asked something last year, they're not going to ask it this year.
So what they asked last year?
We'll go over that another time. And they may still ask it this year, but they ask it with a different nuance. Okay, so sometimes they ask air resistance problems 3 years in a row because they're like, year one, kids sucked. Let's put it back on again. Year two, hey, totally different kind of problem now. Kids did better.
So like, why does the world want us to fail?
Want you to fail. The world wants to test your knowledge. It wants you to show that you know. Okay, and if you can't show that you know, then it will certainly continue to test you. And so it is not about making you fail. That's a little pessimistic. It is about making you show what you know. All right, energy is the most central theme in all of physics. There's nothing more essential in all of science, honestly, that unifies all the fields of science together than energy. Energy is just a number. It's a number out there that we use to keep track of something in a problem that tends to stay the same from the beginning to the end of the problem. And so energy is convenient. Energy is not like time. Time is actually a thing. It's a real physical thing. Distance is the thing, a real physical thing. Energy is not like that. Energy is abstract. It's what you get when you multiply a kilogram times a meter divided by a second squared. Then you get something called a joule, which magically in chemistry, biology, and physics is conserved. Okay. All right, don't forget about any of the terms. There's like a long list there on the next bullet. Look for it, please. It's where it says KE rotational plus UG initial plus KE initial, that's the linear translational kinetic energy, plus US initial plus work, which could be plus or minus work, equals all the same things final. Please don't be one of those students, a lot of you were at some point this year, where you just totally forget to account for one of the kinds of energy. You write down a conservation energy statement, and you're like, oh gosh, there's a spring. Oh, it's turning and moving. I gotta use both kinetic energies. Darn. Don't do that. Just make a note to yourself. If you're the kind of person that tends to do that, make a note and say, ask yourself the question. I should look for 1, 2, 3, 4, 5. I should look for 5 kinds of energy. Okay, 2 potentials, 2 kinetics, and work. I should look for all of them. Okay, every single time I want to use conservation of mechanical energy. All right, I'm kind of done here. Last thing I want to talk about, if we go all the way down past all the examples of energy and the formulas and stuff, it mentions for a conservative force, you have a potential associated with it. This has been something that has come up over and over and over in class, and we mention it, but it's something that's missed over and over on exams, and so I just want to slow down for 10 seconds and remind you. Okay, that there is a relationship between a force and a potential. Okay, for every force field out there, there can be a potential that drives that force. A potential that tells you if you're moving in this force field, how much potential are you gaining or losing? All right, this formula is on the formula sheet. I believe it is again this year too. It is most years. And you just have to know this. This is also, if you look again at Hooke's law, or you look at the law of gravity, you can actually see how it is kind of there as an example. So these 2 formulas right there, right, are written side by side or one above the other on the formula sheet. You can see how the upper one is the derivative of the lower one, or the lower one is the integral of the upper one. Okay, with certain limits, the negative sign goes away. So, and there's a negative sign here, forgive me. So you can see how they're related. You can do the same thing with the gravitational ones. Okay, all right, I feel your energy low. I feel we're 1 hour post lunch and all of you are in a metabolic coma due to the sugar crash that you're experiencing. Got
There
it.
was Tres Leches cake.
Well, that was
Sorry,
so
Switch's cake?
good.
It was good?
I love good.
Yeah. So were my 2 Torchy's tacos and all the chips and cake.
Stop!
Did you get
I mean,
nookies?
that's not cool.
What?
Did you get nookies?
Torchy's?
Yeah, nookies at Torchy's.
What are nookies?
They're
They're
dessert.
like balls of fried cookie dough. It's so good.
The heck is crazy.
Oh my god, I need
No,
to order
I've
the
never had
things
nookie.
from my advisory.
I've never had
Yeah,
nookies.
you can't mess that up again.
Is that why
I
y'all
did it
didn't
in
have
freshman
canes
year.
last time? You just had cake?
No, that wasn't me. It was freshman year. I forgot to order canes for my advisory, and ever
Okay.
since freshman year, they made fun of me. So for the last advisory party, I'm ordering them canes.
Don't forget,
7.
you
There are
have
7 multiple choice questions. I will give you 9 minutes.
We're not
Go.
gonna make it.
Start at the bottom there with
So
number 18
pessimistic.
and go.
You already
So
finished them.
tired.
Of course you already finished them. Bored.
Oh my gosh, question 18 is tiny.
Shh. Sorry, I was trying to squeeze things in. I'm gonna pause it. 9 minutes. No more.
2 o'clock.
So briefly, Kate, yeah, we have about 10 minutes left in class. So briefly, Kate, over here is the very last problem that we just went over as a group, and I'd forgotten to turn on the recording. And so we have 100 kilograms mass times acceleration due to gravity is 10 times the height divided by 10 seconds. This is just work over time, and that equals 1,000 watts of power. You solve for the h, and you get 10 meters. Then we came over here, and 18 was E, 2 times 2 is 4. The next question is 16. That's going to be letter A, that you're looking for the network. The network is the change in KE. The forces that are making it accelerate upward minus the forces downward. It's that net force that's going to be changing the kinetic energy. Next one is E. E has the most area of those graphs. So I didn't calculate anything on these. I just looked at them. And I just looked and said, hey, that one with the most area of a F versus D graph has the biggest work, therefore the biggest change in KE, okay? And so that's what you're looking for there. Next one is B. It was pretty easy here. It was just a ratio, right? So if you burn half the energy when you shoot up 10 meters, and since this is a linear function with respect to H, you have 10 meters to go.
I don't get that one. Wait, I'm like really confused.
Sure, if half the energy, 50
I
joules,
have that.
gets you up 10 meters,
but I
then
don't-
when you go up and you have 100 joules,
Why do you?
double because it's going to keep on flying up until all the kinetic energy slows down and stops, and it is all potential energy stored in its height above some reference point h equals 0. So when you get to 100 joules, you have twice as much twice as much potential energy of gravity as you did before, so you must have twice the height to
Well,
generate
why
that.
do you use 100?
Because they have 50s in the problem. And they said there's 50 potential and 50 kinetic.
Oh.
So at the top it's
So the
100.
total is 100.
Okay,
So the top, all 100 would be potential, no kinetic.
got it.
So that's why I doubled the 10 to a 20. 7A was pretty easy. If there is no friction whatsoever, there's no rotation. And therefore it'll move much more quickly, and it'll just slide down. You just have potential is gravitation potential is kinetic, and you have an answer. For the next one, I can show it, or I can talk through it, but it's right there, step by step. This is an example of don't forget any of the types of energy.
I did it
So-
right, except for I did my freaking algebra wrong.
Okay? That
That's
happens.
so annoying.
That happens on a multiple choice problem. Okay? That if you do the algebra wrong, it's very likely that distraction is going to be there. Right? Because they've already worked the problem wrong themselves many times and said, which are the most common ways? Let's make those our distractors. Okay? So make sure you have both kinds of kinetic. It is a bit of algebra to plug in omegas V over R. I didn't even know I had to do it until I looked at the answer choices. I'm like, I don't have any omegas. I better slow out the omega.
That's what I did.
And then I had to find a common denominator, which I didn't do correctly.
I
the
don't
first time.
understand why you have to do that. Why can't you just factor V out?
You can, but when you divide by it, it won't look like their answer.
Okay.
You could do multiply by r squared later.
You could multiply the whole thing through by r squared on the left and the right. You could do that. To make it look like theirs, I made it look like this. Okay, this is not the only way you have
That's
to do
so
it.
annoying.
It is annoying. I agree.
Because I got what I think is probably a correct answer, but
So-
it
so
doesn't look like any of them.
Please be phenomenally encouraged. There's 35 multiple choice. If you get 25, you blow 10 of them. You are like, you have a 90% chance of getting a 5 on the test. Okay, so you at 1 out of 3 of the questions almost, you can say, I got it. Oh, I have no idea. I got it. That's stupid. I got it. That looks painful. Skip. I got it. So as long as you're only missing 1 out of 3, your chances of getting a 5 are very high. All right, and so
Everyone says that, but then when like you're taking the test, that all goes away. All those
right,
tests.
sure. So the ones you think I got it, no, you didn't.
Yeah.
So that happens also. So you don't want to just skip them. But I guess what I'm saying is, if you know you're going to blow algebra on 3 of them, okay, that's fine.
Yes.
You can blow algebra on 3 of them, and you're still going to make a 5 if that's all your problem you had, right? You can also not know one topic very well and miss 3 more multiple choice. Okay, you still can get a 5. If you don't know 4 topics really well and you miss 3 on each of those, okay, now you're in trouble. Right now, you're looking at a 3 or a 4, pretty quick, and so your score drops from there. And so you don't want to have too many weak suits when you go in there. You can have 1 weak suit, like you hate torque, or.
But I hate torque and gravity and rotation and
Looks like you're taking
oscillation.
physics again in college. At Trinity. Just kidding. All right, so we're down to 5 minutes. What are we going to do in 5 minutes? I would like to turn the page. Turn the page.
Or premium needs it.
What are we not going to talk through here in detail?
Just biology doesn't. Can we just do it again next class? This has been really helpful for me.
I'm glad it was really helpful for you. Here's what I would like you to do for homework. I would like you to go home and start working through the packet on your own. There is not a lot to this. That is, it has points of review, and I will talk through the bullet points next time. But the multiple choice afterwards, just time yourself. So for instance, I'm going to look at the next topic, springs and oscillations. And I'm counting 1, 2, 3, 4, 5 multiple choice on that page, and then it's done. So every multiple choice, give yourself about 1 minute and 20 seconds. So for 5 multiple choice, think 6 minutes, 6.5. Okay, so set a timer for 6.5 minutes or 6 minutes and see how far you get. And after 6 minutes, you're on the last one, you're doing well. Okay, and after 6 minutes, you're halfway through, you're not going fast enough. That's a topic you're weak in. Make a note. Okay, so I would like you to finish the topics for oscillations and springs, which is 6 minutes of work. Okay, plus you can read through the stuff before that. The topic after that is kinematics. There's a lot of multiple choice for kinematics. Feel free to go through and work every one of them. Okay, impulse, momentum, and then stop. So take the next 3 topics, which again are oscillation, springs, pendulums, kinematics, and impulse, momentum, and in this packet, and I want you to answer all the multiple choice regarding those. When we come back next time, we'll go over those, okay, and then we'll also hit torque, circular motion, gravity, and angular momentum will be done. Okay?
Okay.
Thank you very much.
Thank you.
Congratulations again, you winner. You're good enough.
You're talking to Kay. I
You're
thought you were talking
amazing
to
enough.
yourself.
You're strong enough. And doggone it, people like you!
Hi. You're amazing.
I'm so proud of
Can you
you.
stop?
I am so proud of you too.
Matt wants to be the center of your world.
Well,
Not allowed.
I cried a little when you guys
the whole
won.
period.
Mahek feels
She was yelling.
unnecessary
A lot.
pride for something she
Okay,
didn't
you
do.
know, I almost went. Okay.
Yeah, well, you didn't go. You didn't play.
You're not a real fan.
I almost loved you, Kate.
My parents did not let me come to Waco, but I am there in spirit supporting
No, you're
you
not.
guys.
It's just like everyone says.
Your spirit's here.
Take care.
Cut that part out of